Welcome everyone. For this problem, we're going to compute the center of mass of this particular lamina. We're given that it's occupying the disk of radius 1. This is the equation in the first quadrant. And we're also told that the density at any point is proportional to its distance from the x-axis. All right, so we do need to create the density function based off that information. So let's take a look at the picture. So here's our XY plane, and our lamina is occupying this disk only in the first quadrant. So this is the picture I'm going to draw. This is radius 1. So this is the disk, 1/4 of that disk. Now we also know that the density, let's call it rho, is a function of x comma y. This is going to be proportional to its distance from the x-axis. So we know, let's use k as a proportional constant. So we need to figure out what that distance is. So if you look at any point in this region, let's say it has coordinate x comma y. So if you were to find the distance from here to the x-axis, the distance formula we know is the square root of let's say x2 minus x1 squared plus y2 minus y1 squared. We know that's the distance formula. Now the x coordinates is it's the same point from anywhere from the x-axis to any point in the region. So we know we can pretty much ignore the x coordinates. So that means in the distance from the x-axis, the y coordinate is 0. So we have 0 minus y squared, which will simply be y squared, r equals to y. So our distance from the x-axis is just going to be y. So here I'm going to put that right here. Now we can start to find what is the center of mass for this particular object. So now let's go ahead and write down our formula. So we know that the mass, it's going to be the double integral over this region D. So this is our region D in the first quadrant of the density function times dA. So let's see how we're going to express D. Now, since it's part of a circle, we're going to express D in polar coordinates because it's much easier to work with polar coordinates rather rectangular. So I'm going to go ahead and express D in polar coordinates. D is the region in the first quadrant. So R is from 0 to 1 because that's the distance from the origin to our function. And then theta, it's going to go from positive x-axis all the way around. That is going to be pi. So theta is bounded from 0 to, pi over 2, not pi. All right, so that's how I'm going to express my region D. Let's hold on to that. So the mass of this object is going to be this double integral. Rho, we said it's k times y. So k times y, y in polar coordinates. Remember that y in polar coordinates is r sine theta. So I'm going to replace y as r sine theta. So k times r sine theta. Then we have in polar coordinates, our dA becomes r dr d theta. So our bound on r, we know it's 0 to 1. Our bound on theta is 0 to pi over 2. So that will be your setup for the mass. Okay, so let's finish up the computation. The computation is not so bad. So we're gonna go ahead and do the inner integral first. So I'm gonna first combine r and r. So I have the integral from 0 to pi over 2, then the integral from 0 to 1 of k is a constant, so you can pull it all the way outside. We have r squared sine theta dr d theta. So let's go ahead and integrate this respect to r first. So we have k times the integral from 0 to pi over 2. The integral of r squared respect to r, that's going to be r cubed over 3. Sine theta is a constant, carry it over. And we're going to evaluate this from 0 to 1. Then we integrate respect to theta. You could use some shortcut in this integral, but I'm just going to continue as I'm doing it right now. Okay, so what do we have? We have k over 3. Let's pull that out. When I plug in 1 upper limit of integration into r, it's just 1. So what we're down to is simply the integral from 0 to pi over 2 of sine theta. we integrate that out respect to theta. All right, so what is this going to give us? The integral of sine is negative cosine. So we know this is a negative k over 3 cosine theta. Now we evaluate this from 0 to pi over 2. All right, plug in the upper limit of integration. We have k over 3 cosine of pi over 2 minus k over 3. So it's going to be a plus k over 3 cosine of 0. Cosine of pi over 2, this is 0. So we know cosine of 0 is 1. So we simply have k over 3. All right, so that is going to be our mass for this object. Now we need to compute x bar and y bar because those are the components for our center of mass. So the center of mass for a two-dimensional lamina is the point x bar, y bar. And we know that x bar is given as the moment about the y-axis divided by the mass. And the moment about the y-axis, that is simply the double integral over the region D that the lamina occupies, x times the density times dA. And also the y bar, that is going to be the moment about the x-axis divided by the mass. So if you rewrite this as an integral, this is 1 over m, the double integral over the region D, y times the density dA. All right, so these are the integral we have to compute, and then we are ready to finish up the problem. But we have the mass, so that is the good thing. We're going to substitute them right here. So the double integral also, it's pretty much the same setup because you're looking at the same region. So we're going to set up exactly the same way, except to multiply by this extra factor of x or y, depending on which moment we're looking at. So let's do that. So we're going to find x bar first. That is going to be 1 over m. So if I reciprocate k over 3, that is going to be 3 over. So this is going to be 3 over k because it's 1 over m. Then we have the double integral, and we know our bound is 0 to 1, and then 0 to pi over 2. We do x times rho. Rho was k times y, and then we have r dr d theta, so in polar coordinates. Now I'm also going to replace these with their polar definitions. So let's go ahead and replace them. So we know x in polar is r cosine theta. Let me erase this. So we know this is r cosine theta. Y is r sine theta. Then we have k times r dr d theta. So hopefully you're able to follow all of that. So this is the replacement of x. This is the replacement of y, because that was our density is k times y, and then this is our dA. Okay, so again, k, I'm going to pull it outside, and you'll see this k and this k will cancel each other. So we're pretty much down to something simple. We have 3 times the integral from 0 to pi over 2, the integral from 0 to 1, and all the r's, you can multiply them. This will give you r cubed. We have r cubed times cosine theta, sine theta, dr d theta. Again, you can simplify this integral by separating into 2 separate integrals, but I'm going to proceed as it is. So first I'm going to integrate respect to r, and then I'll integrate respect to theta. So we have 3 times the integral from 0 to pi over 2. When I integrate r cubed respect to r, I have r to the 4 over 4. I rewrite cosine theta, sine theta, evaluate this from 0 to 1, and then we integrate respect to theta. All right, so 1 over 4 is a constant. Let's pull it outside. This is 3 over 4. We have the integral from 0 to pi over 2. When I plug in 1 in place of r, that will just be 1. So we're simply down to cosine theta, sine theta, d theta. All right, now this integral can be done by use substitution. Let u be equal to 2 sine theta, then du will be cosine theta d theta. And that's exactly what we got here. So this integral becomes u. So if you integrate that, you'll have u squared over 2. So we have our final result it's going to be 3 over 4. U squared over 2. U is sine, so this is sine squared theta over 2, evaluated from 0 to pi over 2. Now plug in upper and lower limit of integration. This is 3 over 8. Sine of pi over 2. Sine of pi over 2, we know that's going to be 1 minus 0. When you plug in sine of 0, that's going to be 0. So this will simply just give us 3 over 8. So our x bar for the center of mass is 3 over 8. All right, now let's go ahead and find y bar. So for y bar, the only thing we need to do is set up the same integral, but instead of having x here, we're going to multiply by y, and then we have the density function. dA will be r dr d theta. So let's go ahead and fill that in, and then we're pretty much done with this problem. So this was x bar. So y bar, we know it's going to be 1 over m. So m is, again, we know it's m was k over 3, so I reciprocate that. That will be 3 over k. We have the double integral, same region d from 0 to 1. That's for r. Theta is from 0 to pi over 2. And we multiply this by y, so it'll be r sine theta. Then our density was k times y. Y is also r sine theta. Then we have r dr d theta. So as you can see, this is our extra factor of y. This is our density, both of this. And this is, of course, our dA. Okay, now we continue with the integration. So k is a constant. Again, you can pull it all the way out, and then they cancel each other. So you'll simply have 3 outside of these integrals. Then we have the integral from 0 to pi over 2. Then the integral from 0 to 1. We have sine squared theta. And then the r here, r here, that's r cubed. So we have r cubed, then dr d theta. So again, I'm not going to use the shortcut. I'll just proceed as it is. Integrate respect to r first. So we will have 3 outside the integral from 0 to pi over 2. We will have r to the 4th over 4 sine squared theta. Evaluate this from 0 to 1, d theta. And then I plug in upper and lower limit of integration. I have 3 over 4. The integral from 0 to pi over 2 sine squared theta, d theta. Now for this one, to proceed with the integration, you do need to use an identity. So recall that sine squared theta is equal to 1/2 1 minus cosine 2 theta. So that's the identity we're going to use to finish up this integral, because that's the best way to do this problem. So we have 3 over 4, the integral from 0 to pi over 2 of 1/2 times 1 minus cosine 2 theta d theta. And then you integrate 1 respect to theta, cosine 2 theta, using a u substitution. So you'll have 3 over 4 times 1/2. So that's, I pull out the half, that's 3 over 8. Integral of 1 respect to theta, that's theta. Integral of cosine 2 theta, that's sine 2 theta divided by 2. And now we evaluate from 0 to pi over 2. All right, so plug in our limit of integration. So this is 3 over 8. Theta is pi over 2. And then when I plug in pi over 2 in here, you'll have sine of pi, which is 0. And then when I plug in 0, I will have 0. All right. So this simply comes to 3 pi over 16. Alrighty, so that is our y bar. So our center of mass, COM, is going to be x bar comma y bar, which we found it to be. So x bar we computed to be 3 over 8. That's right here. So 3 over 8. And y bar we just computed as 3 pi over 16. So that is your center of mass for this lamina that is occupying in the first quadrant. All right, that's it. I hope this makes sense. See you next time. Take care, everyone.